Welcome back to Arts Learning. In this video, we'll be going over the 4.1 PDF and only a few select problems, okay? The other problems I have an answer key down for, which you can look through. I'm just going to go over the hardest ones, the ones I believe are the hardest ones. The other ones you can tackle by yourself, okay? So, now, let's start. We're going to start with C4, which states that a student claims a block and tackle reduces the work needed to lift a load. Okay, so first let's go over what a block and tackle really is. It's a tad bit complicated. Actually, what I was trying to say was it's not that complicated. Just the name sounds complicated, but it itself is pretty simple in its nature. Okay, it's just mainly pulleys. Think of it like pulleys. Okay. Then these are fixed. These are movable. So there's multiple scenarios, but this is one of the scenarios, okay? Just think of them as pulleys if it's confusing you. Just a set of pulleys. For an ideal frictionless system, is that true? Does it reduce the work needed to lift a load? Now, for an ideal frictionless system, okay, so it's an ideal system. Does it reduce the work needed to lift a load? What is work? Force times distance, right? And what was the formula for mechanical advantage? The general formula. Force in times distance in is equal to force out times distance out, right? So, the work in here, which is force in times distance in, has to be equal to the work out, right? Which is force out times distance out. So the work is the same. It's just that you either increase your distance to reduce your force. Okay? The work is the same. You're doing the same amount of work either way. It's just that instead of exerting a large amount of force, you're just pulling it a large amount of distance, which trades that for force here. Okay? Then over here, the machine would increase the force and reduce the distance. So the work in is the work out. You're not reducing the work. It's just that you trade force for distance. Okay, so this would be a no. What about B? What does a machine actually reduce and at what cost? Okay, so I just described it, right? The machine makes it lesser force for you, but you need a higher distance. So it reduces force. So B reduces force. And at what cost? At an increased distance, right? It reduces the force you have to exert, but it increases the distance you have to pull it through. Okay? Now, what in a real system is the work you put in more or less than lifting the load straight up? Explain using conservation of energy. Okay, if you lift the load straight up, you just take it upward, right? Just like that. And you counter mgh, which is fine. Is the work you put in more or less than lifting the load straight up? Okay, so basically, they're asking, so in a pulley, right? In a real world system where there is friction here and all sorts of variables, right? Is the work in going to be equal to the work out? So it's actually going to be a tad bit greater, okay? Because remember when I told you that actual mechanical advantage is lesser than or equal to ideal mechanical advantage, right? Which means in an actual system, there's all friction, all sorts of messes, right? So you have to exert more force over a larger distance, of course, but it's still that you have to exert more force, okay? So it's not your ideal situation here. So you would have to put in more, okay? You conserve your energy here, but thing is, the friction removes a lot of your energy, right? So in order to make up for the energy that friction removes, you have to put in more force and more distance, okay? So yeah, that's the problem here. So you have to put in more force. Distance you don't need, but you need to put in more force. Or you could also put in distance, that's also fine. But yeah, you have to put in more work, okay? Alright, so now let's go over, I believe, problem 1. Yeah. And also this PDF is there on my website, ottslearning.com, right? Which I'll put a link to in the description below. And you can access it from there. In the 4.1 section for PDFs on physics. A worker pushes a 25 kg crate 12 meters across the ground. Okay? With the 150 Newton force aimed 30 degrees below the horizontal. The floor has a friction of coefficient 0.2. It's a mu kinetic, probably. Find A, the work done by the applied force, B, the work done by friction, C, the net work, and D, the crate's final speed from rest. Okay, so let me give myself some more space here. Okay, first let's tackle A. The work done by the applied force is what? So first of all, work is just force times distance times cosine theta, right? It's just how far you go in the angle, in your direction of motion. So you might be pushing like this, but your distance is this way, right? Straight horizontal. So we need this component here that aligns with the distance. We don't care about the excess force that is wasted. So here, work is just force, 150 newtons, times cosine 30 degrees, times distance of 12 meters. And if you get out your calculator to do that, it should give you about times 12 times cosine 30. So 1558.85. And what was the unit? Do you guys remember? Joules, right? Because this is newtons times meters here. This is meters, this is newtons. So that's why the units would be this. Alright, so then that's the first part. What is part B? The work done by friction. So that's force of friction times D, right? Now, very common that you might just put down mu times mg, and then since there's no cosine theta here, it just be mg, and then times d, and you solve for the normal force, right? Because this is mu normal, so this would be normal here. But think about it. Is that the only force pushing us down here? Normal force must push us upward, right? It must act perpendicular to the surface and keep us on the surface. Otherwise, we'd be sinking below the surface. And what force is also pushing us down? This one, right? What component of that force? 150 times sine 30. Right? Because this is the opposite side here that's going downward. So the force of friction is mu, which is 0.2, times m, which is 25 kgs, times 9.8 meter per second squared for gravity, right? And then times, so I won't do the d here yet, okay? Because I'm just looking at the force of friction, which is mu times the normal force. And what's the normal force going to be? Is this the only normal force? No, right? Because what you have to keep in mind here is that 0.2 times 25 times 9.8. What's the other force it's tackling? This one, right? And both of these are acting in the same direction. So the normal force has to repel both of them, right? If we can count these both, gravity and this force, as negative. So we can add them together because they're in the same direction. The normal force is countering both of them. So plus 150 sine 30 degrees. Okay, that's your normal force. And then what? Times the distance, right? That's your work done by friction, which seems to be 12 meters. So this should give you, so make sure to put your brackets here, right? Because this could get messy. 0.2 times bracket 25 times 9.8 plus, so 25 times 9.8 plus 150 sine 30, okay, 320. Then that times 0.2 times 12. So about 768. About 768 joules. Again, same unit for work, right? All right, so now what? We have our answer for B, we have our answer for A. So actually I'm going to erase this so I can give myself some more space. Right, 768 joules over here. And then for A, 1558.85 is A. So what about C? The net work is what? It's just this work minus this work, right? Because if I consider right the positive direction, then this applied force here is in the positive direction. Okay, so 1558.85 joules minus 768 joules. That's our net work, which should give me about 790.85 joules. My network. And D, the crate's, so let me put a C here, and D, the crate's final speed from rest. Okay. So, what you have to keep in mind here is what energy is all this work going to convert into? Right, this force applied times distance, or my net work here, that's going to convert into kinetic energy, right? So that's going to be my work initial here, which is this, is equal to 1/2 25 kgs times velocity squared. So this should give me times 2 divided by 25, square root that. It should give me about 7.95 meter per second approximately. So 7.95 meters per second. Okay, because this total work is just going to be, so conservation of energy, right? Remember how the total work is just going to be the initial work, and initial energy is going to be the total energy at the end. Okay, not the total, I mean the final energy. So now let's go over problem number 12. Okay, an 80 kg crate is pushed up the 5-meter ramp shown to a height of 2 meters. The ramp is 68% efficient and the job takes 8 seconds. Find A, the IMA, right? And then B, the force in, which is the ideal effort, but force in ideal, right? Because the actual force in might be different from the force in ideal. C, force in actual. D, the work you put in, so work in. And E, your power. It's been a time since we covered power, but you should remember that it's work over time, right? So first, what's going to be our ideal mechanical advantage? So that's our distance in over our distance out, right? Ideal mechanical advantage is distance in over distance out. In this case, 5 meters over 2 meters, right? Because we rise 2 meters, but we put in 5 meters. So this should be about 2.5 is our ideal mechanical advantage. Our force in ideal. So normally our force in wouldn't be ideal, right? We'd have to put our force in actual. But in this case, it seems we can do that. because it asks for force in ideal only. Okay? So force in ideal would just be what? If you use this ratio here, force in has to be 2.5 times lesser than, right? We're doing a lesser force, but for a greater distance. What's the force? There's the force of gravity, which is going to be 80, right? 80 times 9.5, so 9.8, and about 784 newtons. Okay? And then what we're going to do here is with this, we're going to know that force in has to be 2.5 times lesser than this force out, right? Because this is the force out. We're pushing this block. So 784 divided by 2.5 is 313.6 newtons. Because force in over force out must be equals to distance in over distance. So actually distance out over distance in, right? Then you can just use this ratio. You know IMA is this. You can substitute in and find your values. Okay? So then what are we going to do? We're going to... Oh, actually I wrote it wrong here. Force out over force in is equal to distance in over distance out. Alright, yeah, so it's a bit hectic here, but that ratio is also true, but this is the one we use for mechanical advantage. Okay, this is our B, 313.6 newtons. Our force in actual is going to be our AMA, right? So how do we find our AMA? We know that AMA over IMA is equal to our efficiency, which is going to be 0.68, right? 68% efficient. So AMA is 0.68 times our IMA, which is 2.5. So this should be about 1.7. Okay? So then with the AMA of 1.7, we know that we can calculate our force in actual, right? Or force in over, or force out, keep doing the wrong thing, over force in. I mean, force out has to be greater, right? Because you're exerting lesser force. So force in would be lesser than force out. Is equal to 1.7. So force out, we know what force out is, right? Remember? That's just this force here, which is 784 newtons. So 784 divided by force in. So 784 divided by force in has to be equal to 1.7. So force in is just 784 divided by 1.7, or in other words, 461.18 newtons. Okay, so 461.18 newtons. Now let me erase this so I have more work. I have more space here. And then what's going to happen? If we need the work we put in, right? Work in is force in times distance in. Our force in actually, which is what we need, is 461.18 newtons times our distance in, which is 5 meters, right? We're pushing it 5 meters. So this should give us about 2300, 5.9, which we could round up to 2,306 because it's already a large number. 2,306. And then what's our units going to be? Newton meters or joules. Remember, Newton meters are only for torque. Okay. What's our power going to be? Our work over our time. Now you might be like, well, what work? Work in over time or work out? The thing is, they're both the same, right? So it doesn't matter because work in has to be equal to work out, because that's what like conservation of energy says, right? Your initial is equal to your final. So work in, we can use that here. So work in would be 2,306, like we found, and that would be in watts over. So no, the final units would be in watts. This would be in joules times just joules, right? Times joules, and then that over 8 seconds, which should give us about 288.25 watts. And that's the end of this PDF, but make sure to check out the one that I have on 4.2, okay? Because that one will cover the more harder topics and the more crazy energy questions. But for now, good job. Thank you for listening, and make sure to give me a like and subscribe if I helped you, so I could help others like you and reach more people as well.